Hello, today I'm going to give an overview of Markov models. Markov models and Markov chains are simple concepts which can explain the most complicated real-time processes. Concepts such as speech recognition, text identifiers, path recognition, and many other artificial intelligence tools use Markov processes or simple processes called the Markov chain in some form or another. Classical probability theory deals with the principle of independence, compound probability, and the law of large numbers. In probability theory, two events are independent, statistically independent, or stochastically independent if the occurrence of one does not affect the probability of the other. Similarly, two random variables are independent if the realization of one does not affect the probability distribution of the other. The concept of independence extends to dealing with collections of more than two events or random variables, in which case the events are pairwise independent if each pair are independent of each other, and the events are mutually independent if each event is independent of each other combination of events. The outcomes of a random experiment are known as events. There can be more than one number of events associated with any experiment. A compound event is consisting of two or more number of simple events, like rolling a pair of dice. Compound probability is the probability of joint occurrence of two or more simple events. Either all events can be true at the same time, or either can be true at the same time. When at least one of the events holds true at the time in a compound event, we can say that the events are mutually exclusive. Else, they're non-mutually exclusive. In the 19th century, Sir Francis Galton, one of the pioneers of statistical theory, invented a mechanical device that illustrates how the normal curve arises naturally from a combination of large number of independent random events, or factors. As you may remember, the law of large numbers states that if an experiment is repeated again and again, the probability of an event obtained from the relative frequency approaches the actual or theoretical probability. On the other hand, we have Markov probability theory. Markov chains are based on the principle of memorylessness. In other words, the next state of the process only depends on the previous state and not the sequence of states. Therefore, they don't necessarily follow the principle of independence. They don't follow the laws of compound probability, and it's questionable if they follow the laws of large numbers. Markov properties, only today's information matters for predicting tomorrow. Additionally, information from the past does not tell us more about what we know from today's information. Given the present, the past and the future are conditionally independent. The following is the definition of a Markov model. Any process evolving over time with uncertainty is a stochastic process, and models based on such processes are stochastic or probabilistic models. If the process is both stochastic and the behavior of the model in one time or cycle does not depend on the previous time period, the process is Markovian. Even processes where the previous state does matter can be made Markovian through the definition of temporary states known as tunnel states. The simplest Markov model is the Markov chain. It models a state of the system with a random variable that changes through time. In this context, the Markov property suggests that the distribution of the variable depends only on the distribution of the previous state. And as you see from this chart, the system is autonomous and the system state is fully observable. A hidden Markov model is a Markov chain for which the state is only partially observable. In other words, observations are related to the state of the system, but they are typically insufficient to precisely determine the state. A Markov decision process is a Markov chain in which the state transitions depend on the current state, and the action vector is applied to the system. Typically, a Markov decision process is used to compute a policy of actions that will maximize some utility with respect to expected rewards. Then we have the partially observable Markov decision process. And this process is a Markov decision process in which the state of the system is only partially observed. We also have what we call the Markov random field or a Markov network. And this is considered to be a generalization of the Markov chain in multiple dimensions. In a Markov chain, state depends only on the previous state in time, whereas a Markov random field, each state depends on its neighbors in any of the multiple directions. We also have a hierarchical Markov model, and they can be applied to categorize human behavior at various levels of abstraction. The hierarchical model in each state is considered to be a self-contained probabilistic model. It is useful in many fields, including pattern recognition. So why are Markov models necessary? In conventional decision analysis, models assume chance events. They're independent of each other. You have a limited time horizon. Sometimes events usually do not reoccur. But with the Markov model, what happens if you have a problem where you've got an extended time horizon, say over a week, a month, a year, or even a lifetime? As you know, events can recur throughout the lifetime. Markov models are made to address these problems. So what is a Markov chain? Well, a Markov chain is the simplest of Markov models. It models the state of a system with a random variable that changes through time. It has a set of states. It looks at the transition between states. The future depends on the present, and the future does not depend on the past. It has an irreducible chain such that you can get from any state to any other state in a finite number of steps. You have a variety of states or ways to classify states in a Markov model. You have the recurrent state, which means starting at that state, the chain will return with a probability of 1. It effectively is an endless loop. You have the transient state, which is not recurrent, which means when you start at that state, the chain will eventually leave and never return. And then you have the absorbing state, which is once transitioned, the absorbing state will never be left, i.e., if you had a node that says you die. Once you die, you never leave the node. A Markov chain is called irreducible if all of its states are essential. In other words, all states are accessible from all other states. When you create a Markov model, you define the initial states. You determine what the cycle length is between nodes. You consider possible transition among states. You determine transition probabilities. Then you determine utilities and cost, if cost effectiveness is the analysis for each state. In our Markov chain here, we have the simplest of Markov models. In this two states, we have A and B. And in this state, there's 4 possible transitions. There's A to A, there's A to B, there's B to B, and there's B to A. And over here, we have the probability of occurrence, or the probability of transition for each of those nodes. In this two-state diagram, initially, the probability of transitioning from any state to any other state is 0.5. Basically, you have an equal chance of going across any node. In our example, and with an election example, let's say we have 2 candidates. Candidate A, who has a 55% voter preference, and candidate B, who has a 45% voter preference. So we have a probability that candidate A's people will vote for candidate A. Or basically, the probability of an individual staying with candidate A over a month is 0.7. You have the probability of an individual switching from candidate A to candidate B over a month of 0.3. Probability of staying with your candidate over a month of 0.9, and the probability of an individual switching from candidate B to candidate A over a month of 1. The 4 statements made by the polling company can be structured in a simple transition diagram as you see here. The diagram shows the transition of the current voter preferences. Now, if we want to calculate the probability for winning the election based on voter preferences after a month, we need to do the following calculations. Voter preference of candidate A equals the preference share of candidate A times the probability of A voting for A plus the voter preference share of candidate B times the probability of B moving to A. And we compare that to the voter preference of candidate B, which is the preference share of candidate B voting for B plus the voter preference share of candidate A voting for B. As we can see clearly that candidate A, although has a higher voter preference now, will have a lower voter preference after 1 month. This simple calculation is called a Markov chain. If the transition matrix does not change with time, we can predict the voter preference at any future point. So if we make the same calculation for month 2, you move the 43 and 50% to the or 57% to the initial state here, multiply by the transition matrix, and you get these additional probabilities for the second month. Now we have the classic weather example. So you have the probability of sunny today and sunny tomorrow, sunny today and cloudy tomorrow, sunny today and rainy tomorrow, and the probabilities of cloudy moving to the other transition states and rainy moving to the other transition states. The 3-node transition model looks like this, and here we have the transition matrix in a 3x3 matrix. When the Markov chain is homogeneous, the probability distribution of the next state can be represented with a transition matrix as seen here, and the transition matrices are only interested in the final outcome, not the interim outcomes. We have 2 parts of the matrix, which is the actual matrix here, and as you've seen before, we have the initial probability vector that we multiply throughout the matrix. All numbers are in a range of 0 to 1 because they're probabilities, and the inputs are across the row, so we have 6 and 1 and 3, which equals 1 across this way. So rules for applying transition matrices: 1, the matrix must always be square. 2, the outcomes of each experiment must be discrete states. For instance, we can't have 70% sunny and 30% cloudy at the same time. The transition probabilities must remain constant with each generation throughout the matrix. And finally, each row of the matrix must add up to 1. Transition probabilities that remain constant over time are characteristic of stationary Markov models, aka Markov chains. In summary, any process evolving over time with uncertainty is a stochastic process, and models based on such processes are stochastic or probabilistic. If the process is both stochastic and the behavior of the model in one time period does not depend on the previous time period, the process is Markovian. Future is independent of the past given the present. So the probability of the future given the present is what is typical of a Markov model. So the bottom line, or Markov's bottom line, is if you want to predict the weather, don't look at yesterday's weather. Look out the window. Thank you very much and have a good evening.